Well, welcome back to partial fraction decomposition, except this time we're going to be doing part 2. So we'll hopefully get through a couple more examples using the linear factors. So as you recall from last time, there's a little procedure up here that you look at the integrand and you first take a look to see if it's an improper rational function or not. If it's proper, which means the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, then go straight to step 2, factor the denominator over the set of integers, and then start decomposing into partial fractions. So we did an example. And let's take a look at another example. This one's a little bit trickier than the last one because the leading coefficient of that polynomial in the denominator is not 1. So that makes it a little more tricky, and you need to call up those algebra skills for factoring. So I like to use the key number method. So the key number is 2 times -1, the lead coefficient times the constant. And there are some factors of -2 that add up to the middle coefficient of +1, and they are +2 and -1. So what I do is I use those bingo numbers to rewrite the middle term. So you can rewrite the middle term as 2x minus x, and then the first term you just copy it down, and the last term you copy it down. This is the key number method, and we can talk about this more if you want to get a personal private lesson in that. If you factor polynomials using something called the diamond method, that's okay too. So using this key number method, when I factor by grouping, the first pair of terms has a 2x in common, and when I factor out a 2x, the other factor is x plus 1. The last two terms have something in common, -1. So if I factor out a -1, the other factor is x plus 1. So now I can complete the factoring process and notice that x plus 1 is a common factor, and if I factor that out, the other factor is simply the coefficients of those, if you will, so 2x minus 1. So good news, we're now able to decompose this integrand into 2 partial fractions, each with a linear factor. These are linear factors here. So that means that and it doesn't matter what order, I'm going to put the 2x minus 1 first. So we're going to decompose into these 2 partial fractions, a over 2x minus 1 plus b over x plus 1. Our job now is to get the unknowns. So what do I have so far? I have that the original integrand, which looks like 5 minus x all over the 2x minus 1 x plus 1, x plus 1 after I factored it, can be rewritten as the sum of these 2 partial fractions. Now, I like to clear fractions out. So I'm going to multiply this big old equation by the LCD, lowest common denominator, of all the fractions that appear, which is the product of 2x minus 1 times x plus 1. When I clear fractions, I get what's called the basic equation, and it's going to look like this. If you have the basic equation somewhere on your paper, I'll be so happy. I'll give you a partial credit point or 2, okay? And you'll use the basic equation in order to help you get those unknowns. Okay, so now, what's an obvious value we can substitute into our basic equation to kill off one of the unknowns so we can get the other one? Well, obviously -1, because that'll make the a term go to 0. So if we substitute x equals -1 into this basic equation, the left-hand side will turn into 5 minus -1, and then the right-hand side will be b times the product of 2 times -1 minus 1. Okay, so 5 minus -1 on the left is going to be 6, and that's going to equal b multiplied with what? Negative 2 minus 1 looks like it's negative 3. And so solving for b by dividing both sides of this equation by negative 3, and when we reduce to lowest terms, we get that b is equal to negative 2. Okay, we got one of the unknowns. Yay. So go back to your basic equation and try to figure out what's another value we could substitute for x that would allow us to find a. And I noticed that if I let x equal 1/2 here, 2 times 1/2 is 1, and then 1 minus 1 will equal 0. So I'm going to let x equal 1/2 in this basic equation. So it doesn't have to be an integer. And so when I substitute 1/2 into the basic equation, it's going to involve some fractions here, which are not that fun, but the b term will go to 0. So that's the good news. And then what the heck is 5 minus 1/2? Turns out it's 9/2, and then a is multiplied by 1/2 plus 1, which is 3/2, and then solving for a by multiplying both sides by the reciprocal of 3/2, which is 2/3, and then we can reduce to lowest terms. What do we have? 2 divided by 2 is 1, and 9 divided by 3 is 3. So a is equal to 3. Good news. What does that mean now? If you go back to our little decomposition up here, we have a, so we now know that a is 3, and b is negative 2. So what does this mean? It means that when we put all this together, we really are integrating the following sum. 3 over 2x minus 1, and since b is a negative 2, we'll just go minus 2 over x plus 1. We're allowed to do that. And you're going to use the log rule. So this one's a little trickier than the last example we did, because when we use the log rule with u sub on that first term, u is 2x minus 1. So du isn't just dx this time. Be careful. Du is 2dx. So what does that mean? It means we need to have a 2 in the integrand in order to use the log rule. And this 3 I'm going to pull out in front, and when I put the 2 in, you have to be careful because we're not putting the 2 in for the entire integrand, because this second term will keep separate, and we'll integrate him in a moment. So now this first term is in the format of du over u, which has the antiderivative of ln absolute value of u. And don't forget that we have a constant multiple of 3/2, and so this term has an antiderivative of 3/2 ln absolute value of 2x minus 1. And now we can turn our attention to the second term of our partial fractions. This 2 is just a constant multiple. If you pull that outside, that's okay. And then using the log rule with u sub, you have u is x plus 1 and du is dx. So you'll just have your antiderivative will be the logarithm ln of x plus 1. But don't forget your 2, or your minus 2, I should say. And so now you're done. Although you may notice that in the My Math Lab answers, as well as the answers in the back of your textbook, they usually like you to go a little bit extra here, doing some logarithmic condensation. So if you move the 3/2 and make it a power, make the 2 a power, you'll have ln, the quantity 2x minus 1 to the 3/2, minus ln, the quantity x plus 1 squared, plus c. And now you have a difference of logs, which means you can condense one more step. You'll have ln of the quotient 2x minus 1 to the 3/2 all over x plus 1, the quantity squared. So this is pretty typical when you're doing one of these partial fraction decomposition problems. And that's your second example. Thanks for watching, and we'll see you in the next video.